All right, now we're going to begin Unit 6, which is all about probability. Lesson 6.1 has to do with theoretical versus experimental probabilities, as well as the law of large numbers. So first off, let's just hit up that vocab. I'll go over what each one of those are, actually, right in the very beginning. Theoretical probability is the probability of what should happen. So even without running a test, this is just the probability of what should happen if you know the possibilities of what could happen. So theoretical is what should happen. Experimental probably is probability of what did happen. So you ran an experiment and you found so many solutions to what did happen or what could happen. That would be your experimental probability after you ran the test or after you ran the experiment. The law of large numbers then states that if you repeat the experiment more and more, you'll get closer to the theoretical probability. So let's kind of read over some examples of how that all fits or what that all means. So when all possible outcomes are equally likely to happen, you can find the theoretical probability of an event without doing the experiment. So for example, if you actually flip a coin 10 times, you would be finding the experimental probability of getting heads. So if you flip it 10 times and you get heads 7 times, your experimental probability would be 7 out of 10. We would write it like this. We would say experimental, so I'm going to use an EX, would be 7 out of 10. In a sense, that's like saying 70%. 70% of the time when we ran the experiment, we got heads. Well, in theory, the theoretical probability is that 50% of the time, or let me use TH, theoretically, 1 out of every 2. There's one way to get heads, 2 ways possible, heads or tails. When we ran the experiment, though, we got 7 heads out of 10 flips. So again, this just kind of shows the difference between experimental and theoretical probability. So experimental probability is found by performing experiments and observing the outcomes. If the experiment is run an infinite number of times, or it doesn't even have to be infinity, just a large number of times. If you keep on doing the experiment, the law of large numbers says you will get closer and closer to the theoretical probability. So in this case, 7 heads would mean that we got tails 3 times, so we'd only be 4 apart from each other. If we ran it again, let's say like 100 times, and we were still only 4 apart, that would be 48 and 52. So we'd say 52 heads out of 100. Okay, here we were 4 apart, heads and tails, 3 tails, 7 heads, so they're 4 apart. Here, using 52, we'd be 52 and 48. Those are also only 4 apart, but this 52 out of 100 is much closer to 50%, this 1/2, than this one is. So the more and more you run the experiment, the closer it should get to that theoretical probability. Also, a note to kind of think about, one could say that math traditionally uses theoretical probabilities. So we're looking at this one, whereas most sciences, biology, chemistry, even psychology or sociology, those normally use experimental probabilities. So let's look at some examples of just determining which probability is being used, either theoretical or experimental. We are looking at 2 dice are being rolled, and we want to know the probability that the sum will be 12. So we haven't actually rolled them yet. We want to know what the probability is that they will be 12. Well, we would have to be looking at then the theory to say, well, it should become this. It should come out to this much. So that would be theoretical. That's a theoretical probability. Example B, a baseball player has hit 126 hits in 410 at-bats this season. What is the probability he gets a hit in his next at-bat? So for this one, it looks like we've already ran the experiment 410 times. He went up to bat, and he actually hit the ball 126 of them. So because we've already ran the experiment and we've looked at or observed the outcomes, we would say this one is experimental. It's experimental because we ran an experiment already. Not that we're about to, but we already did. Let's look at this one. A bird watcher observes that 5 out of 25 birds in a garden are red, What's the probability that the next bird to fly into the garden will be red? Again, we've already ran the experiment. We ran it 25 times, and 5 of those outcomes ended up being what we were looking for. So because we've already ran an experiment, we'll call it an experimental probability. We're looking back at what has already happened and using that to determine a probability. And example D, we're looking at a hand of 2 cards that is dealt from a standard deck of cards. What is the probability that both cards are clubs? Now, we haven't actually dealt hand after hand after hand yet. We haven't been going through and flipping over all these cards and saying, okay, now what's the probability? So we haven't actually run the experiment yet, which means we're looking ahead to the future for what it should become. We're thinking, what should these 2 cards actually come out to? So since it's what should happen, it's theoretical. So theoretical probability, and how would we actually calculate it? Well, we usually use P on the outside of some parentheses. That would be called our probability of an event. Whatever that event is, we'll just call it E in this case. So probability of E happening is equal to, it's like a fraction or a ratio, the number of favorable outcomes, so like the ways you can possibly win, over the number of possible outcomes. So just the ways that it could possibly end up. So for example, if we want to find the probability of P2, so that's rolling a 2 when a fair die is rolled. Now a die is just a 6-sided cube. It's what you roll when you're playing Monopoly. There are all the numbers 1 through 6 on there. What's the probability that we would roll a 2? Well, there's only one way to get a 2 out of 6 ways possible. So we would say the probability of rolling a 2 is 1 over 6, or 1/6. Example B then, the probability of getting a 1 or a 6 when a fair die is rolled. Well, how many ways are there to get a 1 or a 6? Every time you roll the die, you can get a 1, 2, 3, 4, 5, or 6. 2 of those ways will work, the 1 or the 6. So we would say that there's 2/6 is our theoretical probability, or we can reduce that down to 1/3. Usually, if you can, you want to reduce any probabilities as low as they possibly can go. So we would say 1/3. 1/3 of the time, you should roll a 1 or a 6. This time, 2 dice are rolled. What is the probability that the sum will be 12? Well, how many different ways are there for all of the numbers on your dice to add up to 12? There's really only one way, and that's if you roll a 6 and a 6. If you roll 6 and 6, that'll add up to 12. It's the only possible way to do it, so we'd say there's only one possibility. So our top number, the numerator, has to be 1. Well, how many possible outcomes are there if you roll 2 different die? One of them, there are 6 possibilities for, 1, 2, 3, 4, 5, and 6. The other one, there are also 6 possibilities for, 1, 2, 3, 4, 5, and 6. So the number of total possibilities would be 6 times 6. There are 36 different ways or different things you can get when you roll the dice. One of them works, one of them, 6 and 6, will add up to 12. So we would say the probability that they will sum to 12 is 1 out of 36. So when you're playing Monopoly, 1 out of 36 rolls should be a 12. Experimental probability. Now, experimental, again, is different from theoretical. It means we're going to figure out what is, possible to happen next based on the fact that we've already ran a test over and over and over. So we want to see the experimental probability given some outcomes that we've already observed. So again, we would say the probability of that event equals the number of times it already happened versus the number of times we did the experiment. So, for example A, suppose there are 2,000 students in your school and 1,158 of them are female. A reporter for the school paper chooses a student at random to interview for the next issue. What is the probability that the student chosen is a male? Now, they gave us female, and we're asking about male, so we need to first find out how many males there are. So we take the total number of students, 2,000, quickly subtract that 1,158, and we find out that there are actually 842 males in the whole school. Now that we know how many males there are, how many there could possibly be, then we'll have to say, okay, that out of the 2,000 possible students would be our experimental probability. 842 out of 2,000 reduces down to 421 out of 1,000. So that would be our experimental probability that the student chosen would be male. Now, normally we might want to say, well, you've got half chance, 50% chance, because male or female, there's only two choices. And we want male, there's only one way to become a male, so it should be 1/2. Well, it's a little bit less than 1/2 in our case because there's not as many boys as there are girls in the school. So that's why experimental might not be exactly the same as your theoretical probability. Let's look at example B. A baseball player has 126 hits in 410 at-bats this season. What is the probability he gets a hit at his next at-bat? Well, again, how many times did we run the experiment? 410 times. How many times did it actually work? 126 times. So we would say 126 out of 410. That's his experimental probability. We can reduce that, though, to 63 out of 205. So 63 out of 205 is the probability that he'll get a hit in his next at-bat. Again, we found that by running the experiment. Normally, you might want to say, well, he can either hit it, so there's one possibility, or he won't hit it, so it's two possibilities. So it might seem like half the time it should be a hit. Well, it's not quite a half because we had to run the experiment to find out exactly how many it was. So again, difference between theoretical and experimental probability. Let's look at our last example for this one then. A bird watcher observes that 5 out of 25 birds in a garden are red. What is the probability that the next bird to fly into the garden will be red? Now again, we've already ran the experiment 25 times, and 5 out of them were actually red. So it'd be 5 out of 25 is our experimental probability. That can be reduced to 1/5. So we would say 1 out of 5 birds, or 1/5 of the time, the next bird to fly into the garden should be red. That would be our experimental probability. Now let's look a little bit more into the law of large numbers. Now, how these graphs work, this one is looking at probability. So if we run the experiment one time, whatever we get, that should happen 100% of the time. So our probability would be 1. Now let's say we ran it a couple times, that's why it kind of fluctuates like this. Now it won't always look exactly like this, but what happened in this graph is we just calculated, or we jotted down what happened after this many trials. So like 5 trials we were here. After 25 times running the experiment we were here. After 100 times running the experiment, our probability looked like this. Now again, over time, the more trials you run, the closer it gets to 50%. So this graph, looks like it might have to do with like flipping a coin or something that should happen 50% of the time, 1/2 of the time. So because after the amount of trials, it got really, really close to 1/2 or 0.5 for our probability, this means that it takes this many times, or it takes a lot of times for our experimental probability to get that close to the theoretical probability. This just shows the law of large numbers. Same thing over here. This one is just showing the fluctuation of the percent. So it should show something pretty similar to this one. Again, over time, they should come out to 0. That's like a 0 change in the percent. They should be both even with each other, about 50% for both cases. So they're not, one is so many more than the other one. So looking at the law of large numbers, we want to say that there are a couple different things that the law of large numbers will tell us. One, if the population is large, so again, if we do the experiment a lot of times, the estimate for the population mean would be better than if the population were small. So this kind of goes back to data, like in our last unit, where if you were going to try to get what the average student said at a school, well, it'd be easier to use a really, really big school. It's easier to find the average when you have a much larger population to work with. If your school only has 10 people in it, then it's hard to get a good estimate for the average, because you might take a poll of 10% of the people, well, that's only one person then. Whereas if there were like 1,000 students there, 10% is 100 students. So you can get a lot more information from getting more people. Let's look at some of the other things it says. If we increase our sample size, the sample mean will be a better estimate for the population mean. Same thing, again, going back to data. If you ask more people, it'll be closer to what everybody says. So if there are, again, like 1,000 students in the school, and first you tried only asking 10, well, that's not going to be as close to what everybody says as asking 100. If you ask more people, it'll get close to what is actually true. Okay, that works for experimental probability. If we flip a coin 100 times, our heads amount should get closer to 50% than if we flipped it only one time. If you flipped a coin one time, well, you're either going to get 100% heads or 100% tails. You won't get 50% one way or the other. But if you flip it 100 times, it'll get close to 50% for both of them. And if you flip it 1,000 times, it should get even closer to 50%. So that's what the law of large numbers is getting at. So let's look at some examples of what the law of large numbers might be telling us. We wish to estimate the mean price of all hotel rooms in Las Vegas. The Convention Bureau of Las Vegas did this in 1999 and used a sample of 112 rooms. So they wanted to find the good, like, average cost of a hotel room, and so they surveyed 112 different rooms. If they wanted to get a better estimate of the actual mean price, which one would actually be true here? So if we wanted to take a larger sample, because the sample mean will be closer to the actual price. Well, that's true. That just means if we survey more people or more rooms, we should get closer to the actual truth, which is definitely true. That makes sense. This statement says we should take a smaller sample because we'll be less likely to get outliers. That is false. Again, if you've got 100 students in school and you first checked 20 of them, well, then you decide, well, maybe let's only check 10 because then we won't get as many weirdos. That doesn't really make sense. That logic doesn't work. You should never take less people to get a more accurate sample. You'd want to take more. So that one does not hold up. This one says take a different sample of the same size because the sample size does not matter. Well, this will give you just as good of an estimate. Your estimate should be just as close as it was before, but it won't give you a better estimate. We wanted to find a better estimate. So if we flipped a coin 100 times to see how many times we'd get heads, and then we said, well, let's flip a different coin 100 times to see how many times we get heads. It won't necessarily give us a better estimate. It'll give us as good of an estimate as before. So it's as good, but it is not better. So this one would actually be false. And that's how the law of large numbers works. That'll actually conclude it for our first video.